All right, so we ended with this idea of heat being kind of like work. So work changes the energy of a system. Heat is the energy that is transferred to the system. We could say the opposite, and when energy is removed from the system, thermal energy is removed from the system, we could say it was cooling. Okay, so we can use the opposite word of heat, and we could say cooling, which is probably a little bit better. Okay, so in the process where we have this constant pressure, if you look at our gas law equation, PV equals nRT, then if the pressure is going to stay the same and the volume increases, the temperature has to change too. So we're going to get into what does that temperature change cause. Here, same sort of thing. If we're going to increase the pressure but leave the volume the same, so it doesn't get to expand or anything like that, I have to, how in the world are we going to cause the pressure to increase? Well, remember, pressure is force per area, and force is equal to like change in momentum over change in time, and momentum is mass times change in velocity. So in order to increase the pressure, we have to increase the velocity. So that means that the kinetic energy of the particles, the molecules, has to increase. Okay, so how are we going to do that? Well, if we look at the average kinetic energy, it was 3/2 K sub B times T, right? And this K sub B was equal to what? The gas law constant divided by Avogadro's number. So that is for one particle in our container. That is the average kinetic energy of a particle. So if I wanted to find the total kinetic energy of all the particles inside the container, what would I have to do to that average kinetic energy?
Multiply it by the number of particles.
Yes, multiply it by n, the number of particles. And so that means that I would be multiplying n times 3/2. K sub b is the same thing as r over NA, the number of the Avogadro's number, times T. And the number of particles divided by the number of moles is the definition of Avogadro's number. So this N times kV we could call the total internal energy of our gas, and we're going to use the symbol because it's internal and it's the energy that the particles have because of their movement, and it's inside the container, and it could be exchanged with the environment. We use the symbol U, which is typically a symbol that's used for stored energy. So it's the energy inside something, stored in something. So the internal energy would be this number of particles times 3/2 times R, and then times N, the number of moles, divided by the number of particles times T, because it's 1 over Avogadro's number, and 1 over Avogadro's number is the number of moles per particle, per particles. So then the energy stored in the whole entire container would be 3/2. The capital N for the number of particles, and the number of particles cancels out. Little n, the number of moles. R, the gas law constant, times T. So by adding energy to the system, we have increased the thermal energy or the internal energy. Okay? Now, there was zero work being done in this process that was isochoric or isovolumetric, the one we didn't change the volume for. But in order to change the pressure, we have to change the temperature, which means that there was a change in the internal energy, which was not equal to zero. What causes that internal energy change is the energy that's added to the system, because if you want to increase the temperature of something, what are you going to do? You're going to heat it up. So you do this heat thing to it. Like you do work on an object, you do this heating process. Okay? And so we can heat it, and the amount of energy transferred, or the heat, would not be zero either. And Q is the symbol for heat, which is the energy transferred. All right, so in this particular process, that means that all of the change in internal energy, the change in temperature, is due to heat, the energy that was transferred into the system. Okay? So what if, so we've held pressure constant, we've held volume constant. What's the next thing we can hold constant? Temperature. So we call that isothermal. Constant temperature. Okay, so let's think about that P versus V graph. An isotherm, as it's referred to, would be a process by which both, because think about PV equals nRT, and if you're going to have a closed system, then P1V1 over T1 has to equal P2V2 over T2. So that means, and anywhere along this process, we should have a constant temperature. So it's a sort of a parabolic shape is really what an isotherm looks like. Sometimes they're estimated to be like a negative slope line just to make it nice and easy for you to find the area under the curve.
No calculus.
Right. So we don't want to have to use calculus when we don't have to, but we can estimate it as being a straight line process, but truly it should be kind of a concave up, kind of like a hyperbola.
What's the isotherm?
Okay, so in order to keep T1 equal to T2, we have to change pressure and volume simultaneously. So if this were a process we were looking at in which we were purposely causing the temperature to remain constant, and this is point A and this is point B, is there work done, and we're going to go from A to B, is there work done by the gas?
Yes.
Yeah, because it's expanding, right? So we could find the work done by the gas. Now, truly, because this is not a constant pressure, we would have to find the area under this curve. Okay? That would, all this blue dotty dot stuff would be the work done by the gas on the surroundings, on the little purple dots we were using to represent the atmosphere or the air around it. Now, that means that there's positive work done on, or pardon me, let's not say on, let's say by the gas. but there's negative work done on the gas. So when you go and you exercise, the goal is for you to take some of your stored energy and move something with it. Right? And so then that energy has been transferred out of your body and used. So that's the idea of like exercising, okay? So let's think about this, the gas as being like the person, and you've got this energy stored because you had some lunch, and now you're going to go push your arms and legs away from yourself and push on the environment. Okay? So now you're at a lower energy state. So we have a lower energy state. But our temperature can't change. This temperature is not going to change. I know. So my exercise analogy is kind of falling apart now because we do warm up, so to speak. Okay, but let's look at our change in internal energy, though, would be what? 3/2 nR delta T. What's the whole purpose of this particular process?
Keep temperature constant.
Keep temperature constant. So that was a lot of spoonerisms right there. So if temperature is going to be constant, the change in temperature has to be zero.
Yep. Mm-hmm.
So the change in internal energy has to be zero. So how in the world where are we going to get this energy to do this changing thing anyway? Like, how can we do this work? How do we get the energy to do it in the first place? How are we going to keep the temperature constant?
Keep it cool, you keep it hot, so you're adding external energy,
right? There's got to be energy added to the system or removed from the system. So there has to be some sort of heating or cooling happening. And so the work done on the gas, the negative work done on the gas. So that means that this negative work that's done on the gas, because the gas was expanding, and must be equal to any energy that was transferred to the system. Okay? So that means that Q plus W is 0. Right? Where W is the work done on the gas, but I've added it to both sides. And what was 0? That was the change in internal energy. So the change in internal energy is Q plus W. This is the first law of thermodynamics. So if delta U is the change in internal energy, Q is the heat, and which may just be easier to call it the energy added or removed by heating or cooling. And then W is the work done on the gas. And remember that we wrote that as work was equal to negative P delta V as the work done on the gas. So when the volume changes positive, there's negative work done on the gas, because the gas is transferring some of its energy out of its system to something else. So that's what work does, transfers energy from one system to another. When the volume change is negative, then the work done on the gas would be positive. Okay? Okay, now there's one more process, and it is an adiabatic process. And that means no energy is exchanged and I just sounded like I was going to continue something, but no energy is exchanged. That means that Q is equal to 0. No heating, no cooling.
So temperature is just like constant.
Not necessarily. That is why I'm going over this. Because if the first law of thermodynamics is delta U is equal to Q plus W, so the change in internal energy is equal to, so think about this, the change in internal energy is equal to the amount of energy added plus the amount of work done on the gas. So the change in internal energy of the gas is due to the amount of energy added to the gas, positive heat, or the work done by the gas, and work done by the gas. So if Q is 0 for this adiabatic process, then that just means that the change in internal energy is due to the work done on the gas. So if change in internal energy is due to a change in temperature, then you can still have a change in temperature and have no energy exchange with the environment, no heating, no cooling. Yes, how? So the pressure versus volume graph looks a lot like the isothermal process. But it's just shaped a little bit different. Usually it's like isothermal, and then you'll see an adiabatic, and then isothermal, and then adiabatic. So, for example, you could have a process where it was pressure versus volume, and this is isothermal, and this would be adiabatic, this would be isothermal, and this one would be adiabatic. So see how similar it looks? It's okay. Don't make too many ugly faces. It'll be all right. Okay. So that adiabatic process is like insulated from the environment. There's no energy exchanged with the environment. So now that we've discussed this whole first law of thermodynamics, we go back way up here to this first process where there was negative work done on the gas. The volume was increasing. The pressure stayed the same. What happens to our temperature in this isobaric process? The temperature increased, right? So if the temperature increases, then what happens to the internal energy of the system? Does the internal energy of the system change?
Yes.
Yeah. Right. So we will have a change in internal energy. Is there work done by the gas? Pardon me, on the gas? When it expanded? It was a negative amount, but there was still work done on the gas. And so in order to have this change and work being done, then there probably has to be some sort of energy exchange with the environment. So think about the lab that we did where we kept the volume the same. Okay, we put it on a hot plate. We put it in a cold water bath. So we were doing the Q. We were heating and we were cooling. And we saw a temperature change. And if we allowed the syringe or the object to expand, then we would see work done. But we didn't in that experiment per se. So we can still apply this first law of thermodynamics to every one of our processes. Every one of them. So then down here, where the work done on the gas was 0 because there's no change in volume, that's where we got that O, the first time we saw that delta U, that change in internal energy, was due to an exchange of energy with the environment, due to heating or cooling. So in this case, the energy we add, the heat, okay, or the cool, right, causes the temperature to change. But that's not the only thing that can cause temperature to change. By doing work on the gas, we can cause the temperature to change. It's a lot of stuff to think about, but we're going to practice and see what we can do with them. Okay?